Okay, analysis of a GE 40-watt light bulb. Interesting. They claim it's got a 15,000 hour life. They give it a 5-year warranty. They say it lasts 13.7 years. So what's going on? Let's see. If they look at the fine print, they actually claim that the service life is 3 hours per day. And the warranty is only for 5 years at 3 hours per day. And that works out to about 5,500 hours. So their warranty period is certainly considerably less than what they think the life of the bulb is. Okay, let's check the basics out. The carton said it was a 7.5 watt bulb. It looks like it's drawing just a wee bit less. On the power factor, it's pretty close to unity, which is a sign there's probably power factor correction in the bulb. Now, we look at the bulb itself. You can see there's three very distinct lobes. That's because there's 3 emitters. And obviously it looks like there's some dead zones on the sides here. And then, of course, the front doesn't look like there's any light coming out at all. So this bulb definitely doesn't look very promising in terms of being omnidirectional around its axes. But we'll put a light meter onto it and actually measure it. One way to prove that, though, is to draw a semicircle and get a light meter and hold it very constantly along the radius here and map it out on every 10 degrees. Map the number along the radials here, of course, and that'll give a good indication of the bulb's intensity. Okay, so here's the intensity graph. As you can see, it's not a semicircle going along constant radius as you would see with an incandescent bulb. It's quite irregular. And that's really a good indication of all the hot spots you see in the bulb when it's just simply powered up. Okay, so here's the bulb. Obviously the top's been removed. You can see, of course, clearly 3 emitter panels, obviously giving the bulb a great degree of directionality. Now you can see also that I've got a scope probe and an instrument in one of the panels, so we can take a look at the voltages on the panel. Okay, so here's the voltage going into one of the emitter arrays. You can see the scope saying it's about a 16.4 volt RMS. There's a bit of AC ripple, though, imposed upon it, almost 2 volts peak to peak. And if you zoom in and ask the scope to measure this frequency, it turns out to be about 120 hertz. This is a sign that they have sort of an incomplete filtering of the voltages, and this little bit of ripple, I wouldn't be surprised as the bulb ages and the filter capacitors become weaker for the ripple to become larger. Okay, wow, so many pieces. This is obviously not a bulb that would win the race in terms of low BOM cost. There's, of course, the diffuser. It's made out of plastic, which is unusual. The other previous bulbs are torn down. We're using a glass. You can see, of course, these are the emitters. They consist of essentially a circuit board with an aluminum base for heat reasons. And then it's been attached to, yet again, another piece of metal here. So lots of moving pieces for this bulb. It's obviously an expensive approach. The DC to DC converter, pardon me, the AC to DC converter, of course. Interestingly enough, they put the little electrolytic capacitor, the one item which probably has the shortest expected life in an assembly, up near the top here, and they put in a little tiny hat, which I think is going to probably be thermally the coolest place in the bulb's construction. Obviously, another base here consisting of plastic, and of course the Edison socket back here. Okay, so this is the power module that was in the base of the light bulb. Really traditional approach. AC input here, obviously DC output here, going to each of the 3 emitters. Looks like an isolated power supply with a transformer here. There's a switching regulator down here. Flip it over here, we'll probably find a full wave rectifier. Yeah, sure. Here's a full wave rectifier, so AC in, full wave rectified. A DC to DC switcher with, I would presume, an isolation transformer. And then, of course, the part which will always fail is, of course, the capacitor. Now, as we saw with the construction of the bulb, actually took a lot of effort to put this capacitor in an area which would have low thermals, or the lowest thermals possible, I presume, to try to extend the life. Now, of course, you might be thinking, why don't they just not use capacitors which have very short life? And, of course, it's the standard answer of economics. Electrolytic capacitors are just very inexpensive. Now, there are some fun things you can do when you see a circuit board. For example, down here we can see a UL mark, and below that, let's wait for the camera to focus, is a number. Now that number E whatever, you can actually type that into a UL database, and it will pull up the data sheet for the company which manufactures the board. And actually, in this case, it looks like the raw board manufacturer and the assembly house may actually be the same company. Now, here I'll just pull up the JPEG, the screenshot of the company name, the UL database. So it's interesting sort of thing you can do with industrial archaeology is look at things like that and find out where things are made. Okay, so obviously the pattern there in light dispersal wasn't very even. There's clearly much stronger bulbs in the market. The Cree bulb and the Phillips bulb that I tore down previously were much better in that regard. There are actually a lot of parts inside of it as well. If you look at the bill of materials, and that of course translates into a high price. I bought the bulb on half price sale. I think it was around over $28 original list. And that of course is no longer competitive with Cree now coming in with a 40-watt bulb under $10. So it really shows you just how competitive and fast moving this market is, and how quickly people are improving on the basic idea. So